The first question is from Usanele, and it is question 3, vertical projectile motion. And the question says we have a stationary rocket. Now, I love analyzing the question first before I actually start answering. We have a stationary rocket. Remember, guys, if something is stationary, it is not moving. Now, going back to projectile motion, as well as forces, work energy and power and so forth, if something is stationary, then the initial velocity of that object is then 0. So remember, if something was pushed or something was shoved or something was thrown, then we do have an initial velocity. But if something is stationary, it's not moving. If something is released, the initial velocity is 0 because no force was actually applied to actually make it work. So a stationary rocket on the ground is launched vertically upwards. That means it is going down, is going up. Now remember, something that is going up, we always know what goes up must come down. We have gravitational acceleration, which is actually acting in the opposite direction. Now, another thing, when we're doing vertical projectile motion, if something is going up or an object is moving up in the opposite direction, we'll have gravitational acceleration, which means we have to choose a positive or a negative direction. Remember, if your final answer is a positive or a negative, it resembles what you actually chose as positive and negative initially. And that is then how we choose direction. Also remember, if something is moving up with a certain acceleration and you're also making your gravitational acceleration positive, it means we have two forces moving in the same direction, meaning we are adding them. But if you have it in the opposite direction, they are to be subtracted. I want you guys to think about Newton's laws. That's what we're using here. So it's launched vertically upwards, and after 4 seconds, the rocket's fuel is used up, and it is then 225 meters above the ground. At this instant, the velocity of the rocket is 112.8 meters per second, and the diagram below shows the path followed by the rocket. We must ignore the effects of air friction and assume that G does not change during the entire motion of the rocket. Now let's look at this rocket and analyze it. It started off here. I know that my initial velocity was 0 meters per second. It went all the way up. We know from the time it moves here all the way it moves here, it took a time of 4 seconds. And then all of a sudden the fuel ran up. When the fuel ran up, we know it has that velocity and it had traveled that distance. Now remember, all of this information is going to help us. Another thing we know, if something goes all the way up, we've got final velocity here, and final velocity here will then be 0. Remember, if we use this as final velocity here, the ball coming down, we can then use that as initial velocity. Why is final velocity at maximum point 0? If you throw something up in the air, we don't really see it, but it really does happen. It has a split second and then it changes direction. That split second there makes our maximum velocity, our final velocity at maximum height a 0. So always keep that in mind. Another thing we always need to remember, if an object moves from a starting point coming back to the same starting point, we will have the time up equal to the time coming down, only in opposite directions. Same thing, the velocity going up will also be equal to the velocity coming down, only in opposite directions. So what have I done here? I looked at vertical projectile motion and I looked at the laws and the rules that can actually simplify vertical projectile motion for me before I actually start answering the questions. So let's look at our first question and let's see what it has. So number 3.1 says we must write down the direction of the acceleration of the rocket at this point. Now, it's very crucial to understand the certain terminologies that we are going to be using. We have a normal term called acceleration, right? But we also have gravitational acceleration, right? Which is Fg, which is an object's mass and gravitational acceleration, bringing it down. In this case, do not be confused with acceleration and gravitational acceleration. Here they just want the direction of the acceleration of the rocket at point P. Remember, at point P, the object was actually still going up. It was, remember, if you look at Newton's second law, if a force is applied to an object in that direction, the object will accelerate in that direction. So for P, the acceleration is then upwards. The rocket is accelerating upwards. 3.1, but we're going to answer 3.1.1. The acceleration is upwards. The next one is 3.1.2. Don't get confused with the terminologies. So the next question says, write down the direction of the acceleration of the rocket at Q. Now remember, after the rocket came up here, just going to take all of this off. After the acceleration, after the rocket passed point P, and then the fuel actually started running up. So now what was the acceleration doing? The object was not accelerating anymore. Gravity was not coming into play. And now it was now accelerating downwards because now it is not moving. Remember, the fuel was used up. So now it's downwards. And I always like to say, you guys must use full sentences like downwards and upwards and stuff, and not only up and down, you know? So let's also stick with that. So that was only for 1 mark. And let's look at 3.2. It says, at which point at P or Q, now don't write both, they only said P or Q, is the rocket in free fall, and we must give a reason for your answer. So remember, let me just take this off. How are we going to analyze this? At point P, the object still had some fuel. When it got there, it still had some fuel. When it got there, the fuel ran out. So at point Q, it does not have any fuel anymore. It must then be in free fall. Remember, when you talk about free fall, we mean that it's the downward movement under the force of gravity alone. So only gravity is working on that object anymore, and it's not accelerating anymore. So at free fall, it will be at Q because we only have gravitational acceleration that is now acting on that object. Now, did they say we must give a reason? Let me just read here quickly. And remember, if they say you must give a reason, it says give a reason for your answer for 2 marks. You must give a scientific reason. Don't just say because it's moving upwards. But remember, when we talk about free fall, we can say because the weight is the only force acting on the object. Because weight is the only force acting on the rocket. Let me just spell rocket properly there. So that is then free fall. And if they ever ask you free fall, it's the downward movement under the force of gravity alone. Just in case they ask you, please define free fall, then you also know how to define it. So now let's see what 3.3 is saying. Now that's going for 6 marks. It's saying, taking the upward motion as a positive, use the equations of motion. Now, just going back to equations of motion, there are 4 equations of motions that we can use. And remember, when we do vertical projectile motion, you can use any of those formulas. Always remember, you don't always have to use one, but use a formula that gives you the most information. Most of the time when you have to find first an unknown and then another unknown, it's a little bit risky, but try to find a vertical projectile motion equation that allows you to use it because you have most of the information. We have to calculate the time taken from the moment the rocket is launched until it strikes the ground. So this is what they're asking us, and I'm going to show you how we can then analyze it. They want to know the rocket started off from the ground, it went all the way up here, the fuel ran out. Now they want to calculate the total time, calculate the time taken from the moment that rocket is launched until it reaches the ground. So the time when it goes up here to the time it actually reaches down here. What information do I have? I know that my initial velocity from the ground was 0. It had traveled a distance of 225.6 at a velocity of 112.8 before the fuel ran out. I know I've also got some information from my V final there. Now, I'm going to show you guys 2 ways that you could have actually gotten this equation. However, I'm first going to draw you a picture so that I can show you how you need to analyze your scenarios. So let's look at the first picture first and see how we can then analyze it. So I'm going to just draw a rough sketch here first. So technically, this is how it looks. This will be my ground. So the first thing we could have said, okay, we know that we have to have our final velocity here at the ground. I don't know what the final velocity is. I know that my initial velocity that it started off was 0. I know that before the fuel ran off here, the velocity was 112.8 meters per second. I know that my final velocity here at the top was also 0. What you can do we can use either this velocity and this velocity, or use this as our initial velocity, then find our final velocity. Once you find your final velocity, we can then say, aha, if this rocket traveled at this velocity, what was then the distance that it then traveled, right? They told us from here to here, it had traveled a distance of 225.6. I can therefore say, aha, so it took the rocket a certain time to move from here all the way to down here. I've got that time, whatever the time, let's call that time x. I also know that it took this rocket, it took 4 seconds after it was launched, this rocket's fuel ran out, 4 seconds later. So remember, they want the total time. If I'm able to find the time when the fuel runs up all the way to when it reaches the ground, and then add the 4 seconds, that will then be the total time that I would have reached. Do you see how I analyze it? I used all my information that I have, now I'm going to formulate. So let's find a formula that we can actually work with. So first things first, I can therefore say, remember, I need to find my final velocity of the whole motion. Using a vertical projectile motion equation that gives me most of my information, I'm looking for my final velocity. I have my initial velocity plus 2. I'm going to say g delta y, can also use a. Remember, if it's moving up, we use delta y. It's the vertical motion. If we use x, is then a horizontal motion. I still have vx. Vf, I don't have that one. I'm told my initial velocity is 112.8. Remember, that is squared plus 2. Remember, they told me that I need to take up as a positive and I need to take down as a negative. If my down is a negative, gravitational acceleration is always acting down on an object. That'll be negative 9.8. I'm told that it traveled this distance, but before the fuel ran out, it had traveled a distance of 225.6. So that is my distance, which is, it's also negative. It's going down 225.6. Now, I'm just going to do some mathematics. Squared. Let's put this in my calculator and see what we get. Remember to put brackets in all your information. So I'm going to get 112.8, and that is squared. You can break it up if you feel like you might make a mistake. This is negative 9. This is negative 9.8. And then I also have a negative 225. 225, yes, 0.6, close my bracket, see what I get. This is my answer. I get 17145.6, 17145.6, but I'm not looking for the squared final velocity. I'm looking for VF alone. Remember what you do. To get rid of the exponent, you put both under a square root. This and this will cancel, leaving you with VF by itself. I'm going to put that exactly as in my calculator. Where's my square root? I'm just going to say answer. So now the final velocity that the rocket reaches the ground is 130.94. Remember, we're going to leave it to 2 decimal places. The 1 does not change the 4. Only if the number is 5 and above will the following number change. So then I'm going to get 130.94. Remember, the SI unit for velocity is meters per second. So now I know, aha, so I have my final velocity now here. So my final velocity that it took the rocket at that instant, it reached the ground with a velocity of 130.94. However, I'm still not done. I'm now going to use another equation of motion to say, okay, now that I've got the initial velocity, I've also got the final velocity. I need to find the time, remember? But I also know the distance that it traveled before the fuel actually went up. So now I'm going to equation number 2. Remember, it is for 6 marks. So that was my first part of the equation. My second part of my equation, I'm going to say, let me work it out here. We use a different color. I'm going to say delta y. I'm going to say I'm going to have my V initial plus my V final all over 2, and this is multiplied by time. Why am I using this formula? I'm looking for the total time. I found my final velocity now. I have my initial velocity, but now I also know my distance. I need to find my time. Remember, you can never have 2 unknowns. The distance that this rocket traveled, they told me it traveled a distance of 225. Remember, it is a negative because I had taken down as a negative. So I have negative 225.6 equal to my initial velocity. the rocket before the fuel ran out was 112.8 plus my final velocity of the rocket was 130.94, but remember I have taken down as a negative, so I'm just going to make that a negative. So that is why this is a negative. This is negative 130.94, and this is all over 2, and I'm looking for the time. What time am I looking for now? I'm looking for the time at this point all the way to it reaches its final velocity. What was then that time? So I'm going to do this step by step. Now it's just mathematics. Remember, we always use our math rules and our maths principles, and then you should get the correct answer. What I'm going to do is I'm just going to put all of this in my calculator, and let's see what we get. Open my bracket. So I've got 112.8, 112.8, and that is minus 130.94. Let me just come down, and that is a 2. Just close my bracket there. Let's see what we get. I get negative 9.7, negative 9.07, negative 9.07, but it's still delta t. Remember, if I'm looking for t by itself, you divide both sides with the number that is irritating our poor t, negative 9.0 t. This and this will cancel. I'm going to have a delta t on this side. Let's see what my time is. So I'm going to have a negative, so you don't really have to write the negative because the negative and the negative is going to cancel each other out anyways. 225.6, and I'm going to divide that by 9.07, and then I get 24.87 to 2 decimal places as always. The 3 will not change the 7 to an 8 because if it's a number 5 or greater, it'll then change the 7. So I've got 24.87. I've got 24.87. What time is this? Remember, time is in seconds. What is the time? The time taken from here coming all the way down, it took a total time of 24.87. However, I'm not done. I've only started my time. They're zhoops coming down. They told me before the fuel ran out, the rocket was actually in the air for 4 seconds. The question wanted us to calculate the total time that the rocket actually moved in. So I need to add my 4 seconds to that time because this time here only starts here up to it reaches the ground. So I need to add the 4 seconds here. So I can say total time. I can say the total time is the 4 seconds when it was launched plus the 24.87 seconds of time after the fuel ran out all the way to when it reaches the ground. I can actually do this in my head. So my total time will be 28.87. And remember, the SI unit for time is seconds. So that is the first way you could have actually looked at this problem, right? By finding out to say, I've got this initial velocity, I can find the final velocity, then find the total time. But there's also another way that you can actually do it. So let's look at another method. Another way you could have done it, I'm also going to draw it. First, draw a simple structure for yourself if you feel like you might make a mistake. There we are. And then this is my ground. So we're going to start to where the point is then used up. We know that we have our initial velocity on this side. It is 112.8. I know that my final velocity at maximum height is 0 meters per second. Using this rule, you need to know that time going up is equal to time going down. This means I can then find from the initial velocity here, the velocity that the rocket actually had all the way to maximum height, I can find the time that rocket traveled there. I can then find the time that the rocket had there. We were told it was in the air for 4 seconds before the rocket, the fuel ran off. I can also then say I can find the time that it took from the final velocity at the top going down. So I've got time here, I've got time here, I've got time here. The question wanted to find the total time, which means I'm going to say, let's say this is time 1, time 2, and time 3. Adding all of those together will give me the complete movement from the rocket from this point here, going all the way up and coming back down, right? What do I need to take into consideration? I was given a certain height. I need to find another height. And then there's also another height that I can therefore work with, all right? So where am I going to start? I'm going to start to the point where the fuel is used up. I'm going to use equations of motion. If you say VF is equal to VI plus AT, why am I using this one? I'm looking for my final velocity because that is at its maximum height. I have my initial velocity. Remember, before the fuel ran out, we had at 112.8. I know my A, acceleration, is 9.8. Remember, we had to choose direction. We had to take up as a positive and down as a negative. Gravitational acceleration will be a negative because gravity is always acting downwards for every object. I am therefore looking then for the time that it takes this object to reach its maximum height. So let's see. Final velocity at maximum height is 0. The initial velocity for my object is 112.8 plus gravitational acceleration is negative 9.8 because I have taken down as a negative, and this is delta t. I'm looking for the time. I'm going to take this whole section to the other side of the equation sign. Remember, if something jumps the equation sign, the sign will change. I'm going to have 9.8 delta t is equal to 112.8. I'm looking for my change in time alone. Divide both sides by 9.8. This and this will cancel. I'm going to be left with my delta t. I'm going to put it exactly as it is in my calculator. Let's see what I get there. I've got 112.8. Divide that by 9.8. See what time I get. So I get 11.51 to 2 decimal places. So I've got 11.51. The SI unit for time is seconds. Now let's see. I'm now going to calculate the maximum height to the ground. Let me just use a different color here. I'm going to say delta y. So now we're at maximum height to the ground. I'm starting off here. I'm going all the way to the ground. Delta y, I need to find this distance here so that I can know how long it took it to travel that distance. Say delta y is equal to vi, which is my initial velocity. I've got my delta time plus 1 over 2, my a, and then t squared. I'm looking for y. My initial velocity is 112.8. The change in time, remember what we have? We calculated that it actually went, the whole time going up was 11.51. Now remember, let's say hypothetically speaking, you make a mistake in how to calculate this time here. You do get a mark, you get positive marking for using the correct time, even if yours is wrong in the correct place. You will get positive marking, so don't go and say, I kind of guessed that answer and so forth. Use the answer. The examiner is trying to see whether you understood that that time that that rocket had traveled can actually be placed and using at that distance that it had traveled. Remember that time going up and velocity going up is the same for coming down, only in opposite directions. That is a rule. The examiner is just looking for that, and if you use that correctly, then it's all a thumbs up. So then we have plus, and then I have a half. Gravitational acceleration will give me negative 9.8. Remember, we took that as a negative. And then I'm going to have my delta t. My time is 11.51, and that is squared. I'm going to put all of that in my calculator. If you do want to break it up, you're more than welcome to. Just make sure all your things have brackets, and then you should get the correct answer. So I've got 112.8, close my bracket, it's multiplied by 11.51. I'm going to say plus, this is 0.5, open my bracket, it is a negative 9.8. Remember, we took gravitational acceleration going down. My time again is 11.51. Close my bracket, and my time is squared. So the distance that it had traveled then is 649.7. The 5 will change the 7 to an 8. Remember, it's a number 5 or greater. So here I'm going to have 649.18. The SI unit for distance is meters. But now we're not done. Now we're going to look at the maximum height that this rocket actually traveled. So remember, they first gave us that before the fuel ran off, which was 225.6, plus the height that it actually took at maximum height to the bottom, which was 649.18. Let's calculate what that height is. Once we have the total height, we can then calculate the total time, which is 225.6. So I get 874.78. Remember, to 2 decimal places, 874.78. SI unit for height is then meters. I'm going to use another color. Now we're moving to the last step. Now I know the total distance. I can find the total time now. I can therefore say, if I use delta y, vi delta t plus a half at squared. Why am I using this one? I've got my total velocity. I know that initially, even though the ball had traveled a distance of 874.78, the initial velocity that the ball had at the ground was 0. I am looking for my time and I've got my gravity. So remember, we took distance, we took down as a negative. So this is going to be negative 874.78 is equal to initial velocity was 0. Something that is stationary is a 0. That will be delta t plus a half. Gravitational acceleration is a negative 9.8. This is because we had taken down as a negative, and I'm looking for delta t. I'm going to do it the long way around. I know my kids in my class are probably like, oh my word, ma'am, why are you doing it the long way around? Anything multiplied by 0 will remain itself, and this will give us negative 4.9, I can do that in my head, times delta t squared. Now I'm looking for delta t squared by itself. I'm going to divide both sides by negative 4.9. What you do on the one side, you do on the other side. Like my maths teacher liked saying, if you buy a Mother's Day present, you must buy a Father's Day present. Let's see. Let's put that in the calculator. The negatives cancel each other out anyway, so it's 874.78. I'm going to divide that by 4.9. I get 178.52. Let me just write that down. 178.52 SI unit for time. But remember, I'm not looking for time squared. I'm looking for time. I'm going to put this in a square root. Let's see what we get there. I'm going to put it exactly as it is as my answer. I'm going to get 13.36. Always remember, to 2 decimal places. If it's a number, 5 or greater after the second number, then we round it off. So this is now the total time that this object has traveled from maximum height coming down. Now we need to find all the total time. So I'm going to say total time. Let's start. First, which time are we including? We're including the 4 seconds before the fuel ran out. I'm going to say 4 plus. We are including the 11 seconds that it took the rocket here to reach maximum height. What did we get? We calculated that as 11.51. 11.51 plus. What are we adding? We're calculating this time here. From here, going down, we calculated the time as 13.36, which is 13.36. Let's put that in a calculator. Let's see if we get the same thing. So I'm going to say 4 plus 11.51 plus 13.36. And then, voila, we get 28.87. We get 28.87. And then that's delta t. The SI unit for time is seconds. Just want to go to the previous slide to see if we also got 28. Yay, we also got 28.87 on this side. And then we also get 28.87 on this side. So it is technically at your own discretion how you're going to tackle these questions. But what I would always say, draw yourself a picture and then you think about it logically to how you can actually analyze the problem and how you can actually solve it. Problems like this look complicated, but they're not really complicated. Like I always tell my kids, if you can draw a picture, you're going to understand it much more better. And 3.4 says sketch. Now, my darlings, if you see the word sketch, it means you need to draw. Number one, we do not draw with a pen or a blue pen or a green pen. No, you must use a sharp pencil. You must use a ruler, right? Remember, you must be an architect. It must look presentable and the examiner needs to see full out what is actually going. And as we are drawing this graph, I'm going to show you what other nitty-gritties need to be there so you can actually get 5 out of 5 for this question. Drawing graphs is really, really simple. It's a part that you cannot fail. So it says we must sketch a velocity versus time graph. Most of the time they will give you this, so that's our heading. For the motion of the rocket from the moment, now this is very crucial, from the moment it runs out of fuel. So what does this mean? If I'm looking at this diagram here, my graph should start there. It doesn't say anything about the initial velocity and so forth. Only when it starts there, when the rocket runs out of fuel until it strikes the ground. Now, first things first, it's velocity versus time. I know that the rocket actually runs out of fuel after a certain time. I know that it has a velocity at this time. Let's go back to until it reaches the ground. I know that the velocity is going to reach the ground at a certain time. I also know that the rocket's going to reach the ground at a certain velocity. Now let's see how we can, further the question says. We must take the time when the rocket runs out of fuel as 0. Those are the things that need to be indicated. And it also says indicate the following in the graph: the velocity of the rocket when it runs out of fuel, that was given to us, the time at which the rocket strikes the ground. Now for this question, guys, remember, the time that the rocket strikes the ground was the previous question that we needed to calculate. Let's say hypothetically you got the question wrong and so forth. When you are drawing this graph, you must use that time that you got into this graph when you're drawing it, right? You carry over that answer and you're putting it in there. You are showing the examiner that the time calculated in the previous question is the time taken by the rocket to reach the ground, and now you are presenting it in a graph, right? That's all the examiner wants to see, that you understand the relationship between that time and representing it in a graph. So let's draw this graph and let's see what we're going to do. So first things first, it is a velocity versus time graph. Velocity versus time. Remember to use a sharp pencil. We're going to have a line going like that, a line going like that. Avoid having lines move in that direction. Now, in this side, we are going to have velocity. Now, remember, velocity is measured in meters per second. In this time here, we're going to have time on this line. Remember, time is measured in seconds. Already, I'm halfway there. They say we must indicate the velocity when it runs out of fuel. It ran out of fuel when it was a velocity of 112.8, right? And then they told us we must indicate with the time when the rocket hits the ground. It reached the ground at a time of 24.87. Now I'm going to draw my graph like this, and that should then be together, right? Remember, you had to indicate your distance, your direction, but this is then how I was then to draw it. Remember, the graph must start at 0 and at 11. The graph must be a straight line, no wiggly lines. You can already see mine's wiggly. Make sure you use a ruler. And the graph must have then a negative gradient. This is then a velocity versus time graph.